So good morning everybody. While Urs gave a very general overview about the monitoring activities, I will go a little bit more into detail into a technical issue, and this is the monitoring of the signal in space ranging error, or the SISRAN. So let me start with a short overview about the general concept of GNSS positioning accuracy. Most of you probably will already know this. So the general positioning accuracy sigma is composed of the user equivalent range error multiplied with the dilution of precision. The user equivalent range error is composed of all measurement and modeling errors of absolute range, whereas the dilution of precision provides a mapping of the range error to the position error, and it depends on the geometry of the satellite. So you will probably also know this picture here. If you have the satellites distributed quite close to each other, then you have a bad geometry, you have a large dot, and it will result in a bad positioning accuracy. If you have the satellites distributed quite evenly over the horizon, if the volume generated by these satellites and the receiver is quite large, you have a small dot value resulting also in a smaller positioning. The user equivalent range error can be separated into two parts. The first one is the topic of this presentation. This is the signal in space ranging error. It represents the errors of the broadcast orbits and clocks. And the second component, the user equipment error, is related to receiver noise, multipass, and uncorrected atmospheric delays. One has to add that these concepts use assumptions about that the errors are uncorrelated with a zero mean, and that this is only valid in a statistical sense. As already mentioned, the signal in space ranging error is one of the key indicators for GNSS performance monitoring. It depends on two different components of a GNSS, namely the capabilities of the space segment, mainly the clock stability, but also the predictability of the orbital motion, and capabilities of the control segment. How good is the computation on the ground of the orbital clocks? How well are the monitoring stations distributed, and of course the upload capacity, so how dense is your network of upload stations that you can provide this upload with a pretty low latency. The SISRAN is evaluated by comparisons of the broadcast ephemerates with some reference product, and was already told you something about this. So for GPS at the moment it's quite easy, so one can use the combined IGS orbit and clock product. For GLONASS only a combined orbit product is available, so no combined clock product, so therefore we decided to just use the product of one of the IGS analysis center. For Galileo, Beiru and QZSS there's also no combined product, so again we use one single analysis center product now from the MJAX project. And for IRNSS, there's no product available up to now. You will see on the next slide that we also need differential code biases for some purposes, and here again we use the MJAX product. Let me now briefly introduce the concept of the SISRAN computation. The first step is the translation of the orbit and clock data to the center of mass. We need phase center offsets for this translation for the broadcast orbits. I will show you some more details on the next slide. Then the second step is the evaluation of the orbit differences in radial, along track, and cross track direction. Then the DCBs come into play. So for some systems, for example for Galileo, but also for Beiru, we have to do a translation of the clock signals. Therefore we need the DCBs. Then after this translation we can compute the clock differences, remove an epoch-wise constellation mean, and then in the fifth step we can compute for every epoch I and for each satellite K the SISRAN contribution, and you can see here the equation. So we have here the radial differences, we have here the along track and cross track differences. You see also weighting factors, so this is indicated with this W. And these weighting factors depend on the orbit height of the satellites. We have here the clock contribution and subtracted the constellation mean. After this step, we can do an outlier screening, so we can use some fixed limit, we can use some percentile limits, and at the last step, the scissor can be computed as the RMS over all epochs and all satellites. The basic difference between precise and broadcast orbits is the reference point. So the precise orbits refer to the center of mass, the broadcast orbits to the antenna phase center. So we need the phase center offset, the PCO, but this is of course not the one that the IGS usually uses for the generation of its precise product, but it's the one that is also used in the generation of the broadcast ephemeris. And unfortunately, these offsets are usually not known, and therefore we estimated them as a radial offset between the precise and the broadcast products. You can see here two examples. So for GLONASS, for example, we have two different subgroups of the GLONASS M satellites differing by 40 centimeters. For Galileo, we see some time dependence, so we have here three different periods where the offsets significantly changed. If we have to translate the clock signal, we also need also have an error contribution of the differential code biases, or for Galileo they are called broadcast group delays, and this is an additional quantity entering the error budget. And you can see here an example for the Galileo E1, E5B DCBs compared to the MJAX product, and we have about a standard deviation of 10 centimeters of additional contribution. Just to note that this, if you apply these corrections, this can also be used for a single frequency system. The broadcast ephemeris product we use is the IGS MJAX product. It's generated on a daily basis. We have 37 real-time stations and one offline station covering all GNSS signals, and we have also an additional product for the civil navigation, for the CNAV message of GPS. So 9 Java receivers, these yellow triangles you see on this map, contribute to this CNAV product. Let me now show you some examples. The first one is the orbit comparison for Galileo for April 2017. You see the orbit differences in the three components. So in the radial direction, along track and cross track. So we have about 13 centimeters standard deviation in the radial direction, the smallest one, the largest contribution in the along track direction. And on the right hand side you see histograms of these orbit differences, and you can see that they have a pretty Gaussian distribution, except for the long track component, which has a slight shift. If we have a look at the clock comparisons, here are two examples again from April 2007 for Galileo and GPS. Galileo is basically running the satellites on passive hydrogen masers, so we have very stable clocks. You can see here this quite small scatter. There are also quite frequent uploads, and resulting in a total scissor of only 15 centimeters. For GPS, most satellites are running on rubidium clocks, but there are also two satellites with cesium clocks. You see them here, for example, this cyan indicated satellites with larger deviations, and also the scatter of the other satellites is larger than for Galileo, resulting in a scissor of about 50 centimeters. An example for Beiru, so there was a change in January 2017. This was a revised broadcast generation with the goal of an improved scissor. And you can see here the time series of January for the Beiru 2 IXO and MEO satellites. And you see that there's a change in the middle of January where the offset of the individual satellites is changed. So there's a changed PCO, which is unfortunately unknown, and if you have a look at longer time series, it also seems to be a time variable. So this might be related to a non-physical orbit representation, and we also see some discontinuities in this time series. If we have a look at the scissor over time in monthly mean values, as you can see on the right-hand side, that there is, in particular for the orbit part, you can see some slight improvements in the scissor. If we now have a look at the scissor values of the different constellations, you see some numbers here that you've already seen before. So the 50 centimeters for the GPS. If we limit to only the rubidium clocks, we get an improvement of 5 centimeters. If we limit only to the latest generation of 2F satellites, again, 5 centimeter improvements. You see that the CNAV message, which is still experimental, has almost the same performance as the LNAV. For GLONASS, we have a quite large value of 3 meters for the CISRE, and this is related to the clock differences, or basically the interfrequency biases that are not considered in the CISRE monitoring for GLONASS. So you can see here the time series of clock differences between broadcast and precise products. And if in addition daily interfrequency biases are estimated, this value improves to about 1 meter. For Galileo, we have these very accurate clocks that you can see here that the difference between the orbit CISRE and the overall CISRE is almost 0. Very small numbers here. And for Beiru, we are at about 1.6 meter level for all satellites, and the value is degraded by the bad orbit performance of the geosatellites, where we have correlations between different parameters due to the stationary geometry of these satellites. So in summary, the signal in space ranging error is a key indicator for performance monitoring. Currently, there's no combined IGS multi-GNSS reference product yet. There's also currently no quality control for the combined broadcast ephemeris. I've shown you that we need a common set of broadcast satellite antenna phase center offsets. The best way, of course, would be if these values are provided by the system operators, because they know the values that they use. Alternatively, one can estimate them from the set difference, from the radial differences. And we need some discussion on the outliner screening if we use some fixed values or some fixed percentile. Just an example on the right-hand side for the importance of performance monitoring. These are the clock differences in the middle of May for Galileo, where there was a navigation message outage. And you can see here the degradation of the clock with time. Then we have some outage of the clock messages, and again the general usual performance after that. So that's all. Thanks for your attention.